All right, so here is the parametric radial basis function summarized all on one slide. And as you can see that we are like in the Z space such that we have this linear model, and then obviously we can solve for the linear model. And one thing that we figured was that the number of parameters that are there in my equation are going to be like as much as my data, right? Which makes this inefficient in a certain way, and also overfitting, the chances of overfitting go up. And so we need to address this issue. And the way we address this is by using something that's known as the radial basis function networks. And so let's have a look at them. Let us assume we have some data in 2 dimension, and this is how the data distribution is right here and here. Okay, so these are the points that are distributed throughout the 2-dimensional space. And if we have the idea of the parametric radial basis function, I know that for every point here in this 2-dimensional space, for every point I need to have that bump or that curve. And based on that curve, I have to check that effect of that curve on a test point. Now, if that test point is like a certain distance away from each of them, then I need to kind of calculate the impact of like all of these data points. And so that's making it like really inefficient, and that's a lot of work. How about we can like come up with some point within, and if my data distribution is somewhat similar to this, such that we have these separated data or like clusters of data. So all I can do is I can, if there is a possibility that I can come up with just like one point within each of these clusters, that using which I can have a bump that is representative of this entire cluster. For example, if I come up with my representative point as this point number 1, I can call the bump over that as bump number 1, and then I have to only worry about this bump 1, which is the representative of this cluster, and the distance from this point x. That's it. So similarly, I can come up with like some other points, and these points might represent the data itself, or maybe a calculated value, that's fine. But what we're doing is, if I have this kind of data distribution, I can aggregate the effect of some set of points, which is like some subset of points, because all of them together might be having somewhat a similar effect on x. Okay, so that's what I'm trying to do, locate bumps representative of each subset, which in my case are these clusters, right? And then this is, if you remember from the nearest neighbor, you can tell that this is equivalent to locating centers of each cluster when we were trying to find centers of the cluster. So in this example, we'll have like 4 bumps, right? You can tell there are 4 clusters, so 4 bumps or 4 like peaks, whatever you'd like to call them, instead of like n peaks or that curve that's there. All right. So this can significantly reduce the number of parameters, right? So it can significantly reduce the number of parameters in my model, because now instead of like having to calculate for each one of the data point, what I'm doing is I have these representative points that kind of represent the data within that subset. And so that's how I'm going to approach this problem. So basically what I have to do is, of course, I have to decide how many of these points exist. So the first decision that I have to make is decide number of these curves or bumps, whatever you like to call them. Let's say like k of these exist with centers. They have like some centers, mu1, mu2, and so on to mu k. Now these mu's will be representative of the point of any point within this cluster. For example, if this center is like mu1, so all the points within that cluster would be represented by mu1. And so that's the first thing that we need to do. Second, to find that representative point. So basically, my center, whatever I come up with, should be or must cover the data. That means it should represent the data really well. I don't want that it's like far away from one of the points, but rather it's a good representation of that small cluster. All right. So once I know that the centers that I'm using, for example, once I know these mu1, mu2, mu k, right? Then like I can use my feature transform and see how this has impacted my feature transform. So if you remember my z space was the transform function or the phi, and it was on x minus mu1 now, and x minus mu1 over r, and then so on. We'll have whatever number of centers you've decided, phi x minus mu k. And of course, these are going to be less than the number of data points, because we have one center for a lot of data points. And so this like is a reduced feature transform, right? So it is reduced in the sense that we'll not have as many values as we had for the original one. All right. And one more thing to consider is that the data itself might have like some kind of a bias that we have to deal with many times. And so to maintain that consistency, we will have to introduce an extra term that's known as the bias term. And so finally, what we get is our final hypothesis with the bias term and everything. So let me write it down here. And that is g of x is going to look something like this. This is my bias term. And here in my feature transform, I can add like 1 for that, like corresponding to that, plus the summation of whatever we had earlier. Let's say now I'm introducing this j equals 1 up to k. Why? Because I have k centers. So I'm replacing something which is my phi x minus mu sub j of r, instead of the xn's that we have. So now this in turn, let me write it here only, is W transpose. So similar to this form, this is like W transpose Z. So what do we have here? We have the linear model, provided I have these centers, because these centers are actually determining the components of my feature transform. And if we look at the parameters, like how many parameters do we have in this equation? So of course I have like these W's here, right? And then I also have these mu J's, the centers that we decided for different clusters of my data. And both can be varied so that we can fit the data. Now, if we look at this equation itself, it's like g of x, right? We can tell that this like mu j, this thing is nonlinear in mu j, right? Or another way of saying this is that this is explicitly nonlinear. Why? Because we get to choose like what centers are the values, like what are the values of these that represent my data really well. So basically, I am tailoring the features to the data such that like this kind of interpretation allows me to formulate an algorithm for selecting the bump centers, because I am impacting it in a certain way, right? So after selecting those centers, like these mu j's, these mu1, mu2, and so on, you will have a linear model. So that's a better way of saying that. Like after selecting these centers, these mu sub j's, this mu sub j's, I will have a linear model. Okay, so let's like explore this model a little bit more, and I'm going to do that using a pictorial representation. And like the big leap that we have made here with this like parametric radial basis function network, and by the way, maybe I forgot to mention that now this is the parametric radial basis function network. This is what it is. And so what have we achieved with that? What we have achieved is that we have reduced the number of bumps when transitioning from the original model. And that's a fundamental idea. We have reduced the number of parameters that we need to take care of in this network. And so let's look at it again. And let me write it again as well so that we understand it better. So my g of x is my w0, the bias term, and then the number of centers is the j up to k. That's what we decided, right? And then the phi x minus mu j over r. All right, so here, this is my similarity feature, because I'm trying to find the difference of a certain point from the center of some subset, which is usually a cluster. And let's see like how we can use to solve problems, right? So let us assume I have like a test point x, right? And so what I do is I have to pass this through some similarity measure, which is like my feature transform, of course. And so that's like, first I calculate this. So for example, this is mu1, the first center for any whatever center you decided, over R. And then what I do is I pass it through this phi, whatever that function is, right? And then apply the weights here. So this is W1, right? Similar to that, I'll have it for like other mu's, whatever mu's I've like to come up with. So maybe this is x minus mu2 and over R, and this is some x minus mu k over R, and each of them will go through this kernel, which is my phi, right? And then because this was augmented, remember, with this W0, and so again, first of all, let me apply the weights. So this is like WK, W, we are summing them up, right? So that's why I'm like taking them together. And so let's assume there is this like W0 weight, and all of them finally, when summed up, arrive at this point, which is nothing but my g of x. All right, so this is the reason why we've been calling this like a network, right? As you can see that here is essentially an, or like even a better way of like representing this is that here you can have some kind of a, like maybe g of x is outside this. And here maybe you have some kind of like a transformation again in terms of like, it's not something difficult to I would say relate to, because let's say this was a classification problem. So maybe I'll have like a sine function here, or if it was a logistic regression problem, then I'll have to find, like I'll have the sigmoid, and then I'll be finding the probability and so on. And then if it was none of them, then I would just like sum them up and get g of x because it was a regression problem and so on. So that's the pictorial representation. And this kind of tells us why we've been calling this like the radial basis function network, as you can tell. Okay, so this gives us an idea of how we'll be using this. But one like mystery sort of that remains is like, how do we fix the centers? Because like once we fix the centers, then we have like a linear model in W, and then I can use all my knowledge of the like the linear model and do things, right? So how do we like get these mu's, right? The big question is that. So let's try to figure that out as well. Okay. So a couple of observations regarding how to fix the centers. In fact, like this is the procedure usually followed. So fix the center to the centers of clusters in the data. And by the way, like we are assuming that this is like well structured data in terms of like there are clusters. And if not, we know an algorithm that like that we spent some time on last time that finds the centers for like data, and especially very well for tightly bound, well separated data. So we will find, first of all, the centers of clusters in the data. And most likely can use Lloyd's algorithm, if you remember from last time. Oops, Lloyd's algorithm. And one thing to notice here is that if we are putting like centers, we need data. So it depends on data. And it's not using y values. When we are doing this process of finding the centers in this scenario, you're not using y values. It's completely based on our data, like the input distribution of my x values. So we cannot say for like sure that we are fitting the data as such, right? The real aspect of data fitting will come into picture when we are trying to find the W's. So for now, it's outside that. And so this is like a way of, this is an unsupervised step, an unsupervised learning type of a scenario. Because we are not using, as I said, y values. So unsupervised, I would say, step in this algorithm, which obviously we haven't talked much about. And so this is the first time we are really looking at what's going on. I'm not looking at what my y values are for my data, but rather I'm just like looking at the input distribution of my data. So that's the first point. The second point is now finally you have a linear model once you have decided these centers, right? So you have a linear model. You have a linear model with linear in these W's, right? The weights that you're going to come up with. And of course, you have like similarity features. And based on this linear model, you can use any algorithm depending on your application. For example, you can use pocket algorithm for your classification. So PLA or pocket algorithm for your classification, pseudo inverse for regression, and then of course gradient descent, minimizing the cross entropy error for logistic regression. Now this is the radial basis network. It's a linear model, and what we're doing is we are beginning with finding the center of clusters, and of course using any known good algorithm for doing that. And this is important because this is like an unsupervised step in the sense that we are not looking at the target values, we are only looking at the data. And once we have that, we have a linear model that we have like known techniques to solve that. Now, a small unknown part still remains. What about these R's? Like, how should we be picking these R's? Is there like any kind of suggestion about it, and so on? And so let's look at like picking these R values, the scale parameter. Picking R values. And so we're picking these R values because of the shape of the bump, right? So there will be K bumps in D dimension because let's say there are K centers. So K bumps in D dimensions. Okay, so if radius of like if R equals 1 for of data, and then the volume that's like covered by a bump, by one bump, volume of data covered will be like almost R to the D, right? And so for all K bumps, it's going to be for K bumps or curves, it's K times R to the D. And you want this thing here, to cover your entire data, right? And so if the data set has a bound of, let's say, some R, then you would want this KR of T to be almost equal to that R, which means my R is going to be R over the dth root of K. Right, so this is the rule of thumb that my R has to be somewhat close to this value, especially like R being like inversely proportional to the dth root of K. All right, so this is about how should we picking out. This is like a recommendation, of course. Different things can still be tried depending on the problem that you're solving, depending on the data that you have. So having said that, we have a technique of fixing an R. We have some ways of finding the centers of clusters from where we begin, because that would be step one. And so now let's look at this and let's summarize this first, I would say. And then we'll start looking at some of the results that we have like from real data. So this is how this radial basis feature transform works. And so what we're doing here is, I think we already talked about this. Like this is like getting the feature matrix and how we have like instead of these, we have like these mu's. These are the centers essentially, and we are introducing like this augmented value and how to solve it for different problems. So I think we already addressed all of them. This is just like putting everything together. So moving on, as I said, let's look at this experiment wherein we have this data, and I think we've looked at this data before. And the white curve here is my target function. So the white is the target function, and the blue is the fitted curve. Okay. In the first one, my parameters like the input values are k equals 4, so 4 centers, and then r is exactly equal to 1 over k. Okay, that's fine. That means d is just 1, and that's fine. That makes sense because we have like x, y. Okay, so what we have done here is that we have tried to fit the linear model, as you can tell by looking at this equation here, and like regression problem, of course. And you can tell that like this is fitting, of course, and it's like quite a reasonable, I would say, fit, right? It's quite a reasonable fit with k equals 4. Now here on the right hand side again, d is again 1, so r is exactly equals 1 over k, and k is 10. So then 10 is larger than that, r goes down, and then using this k equals 10, we are trying to fit again the linear model. And as you can see, we have like more centers, right? Because we said that k should be greater, right? And r is smaller. And so this is, you can tell, not a very good, I would say not a good approximation of my target function. That's like the white curve. And overfitting is happening, and extreme overfitting is happening. If you can just like look at it, it's trying to fit the noise, as we know the definition of overfitting. So what should we do? What is the solution to this problem? Well, just by looking at this picture here, I can say that we can reduce k, right, the number of bumps, because that is like giving me this like extra overfit everywhere. And so maybe you can do that. And then that is an area of ongoing research. A lot of research is going in that direction, that of course trying to find the best k. The other thing that we can do is, of course, find the best value of k through cross validation. And anything else that you can think we can do here, because overfitting is happening, and overfitting should ring a bell here, that yes, we can do something, our good old friend regularization, right? We can, because all we're solving is a linear model, and regularization works really well with the, as we have seen. So let's see what happens. So here, and if you remember with the regularization, we can keep the flexibility of the more complex model and still try to kind of control it based on some regularization parameter and then try to fit the data. So this was the one where overfitting was happening. And with some regularization with the same exact parameters, but like regularized this time, as you can see, it fits really well, right? It fits better, I think, than the earlier one. It takes care of like a lot of other points. So this is the like one very good solution to overfitting, even when we are using these radial basis networks. All right. So here we saw that regularization helps fight overfitting even in this scenario. And finally, putting everything together. So here, like just to summarize, what we did was we derived the radial basis function network, right? And we also figured it's a soft generalization of the k nearest neighbor rule, right? In terms of like the way we were finding those k centers, and then based on that, like deciding which one lies closer to that center or not, right? So that's why we say that's a soft generalization of KNN rule. This additionally, in addition to how we did it, it can be derived using regularization theory or a noise interpolation theory. So that's extra. Uh, Depending on the problem, you can use non-parametric or parametric version. There is no like restriction as such. Again, depends on the problem that you're looking at. And once you have the centers, so that's what's saying, given the centers, it's easy to learn the weights, because then you have a linear model. And that's the important accomplishment, I would say, right? And a linear model with an adaptable nonlinear transform. Why? Because depending on the centers, we can like have different values for the feature transform. All right. And until now, we use like all uniform bumps, right? We can have different shapes for this, like matrix, for example, for the Gaussian kernel, one way is like using the covariance matrix and so on, right? So there are many choices apart from, so basically telling you that you're not restricted to just like using the uniform bump. And finally, how to better choose the centers. And that kind of takes us to something that's known as unsupervised learning. We saw some of it when we were selecting the centers based on the method that we outlined. So basically, we'll try to understand how can we make the tools such as like the branch and bound more useful when like when I don't have labels, when I don't have the y value. So how can we do that? And even like that's going to be the topic for next lecture. This is just like showing you on, as the heading rightly says, peek at unsupervised learning. We saw this like in the 21 nearest neighbor, how we were able to classify. So this is like the multi-class problem. And we said that with the k nearest neighbor, the multi-class problem works really well, right? And as you can see on the right hand side, it works even better in this case, right? It clearly, this is like unsupervised learning. We are clustering based on like some similarity measure, of course. And what's happening is it's able to cluster like all 10 clusters because there are like 10 digits. So this is the power of unsupervised learning that we are going to most likely look at in the next lecture. So that's it for today's lecture. Thank you so much.